In this video, we are going to discuss about spherical aberration. Now, what does the term aberration mean? In most of the cases that we have considered in case of the images formed for mirrors, especially what we were dealing with in the previous video, the images were formed at a single point, thereby giving a very sharp image. But that's not the case every time. In most cases, what we have considered as of till now is that all the rays that are incident on a spherical mirror, they are in a parallel direction and they meet at a single point. But however, and obviously they are more or less the paraxial rays, and they have a very small aperture for the given spherical mirror. Aperture that we had considered was obviously the uh, linear and the angular aperture, which are always considered to be very small in compare when we are dealing with the single point images that are formed. Just let us consider a case where a mirror that we have placed, a spherical mirror that we have placed. Let's suppose we have a spherical mirror that's quite a big one I have drawn, and we are considering, so that means obviously we have the linear aperture to be very large as compared to the ones we had considered as of till date. Now, this is the shaded portion of the mirror, or and the other side is obviously the reflecting side. And in such cases, what we come across is that we will consider two sets of rays. Now, as I mentioned the term paraxial, the term paraxial means that they are closer to the principal axis. The principal axis that I'm drawing right now, we had already discussed about the principal axis, and the paraxial rays are simply closer to, are parallel and closer to this principal axis. Now, in the previous cases, as I said, we had always considered the paraxial rays and the aperture was very small, let's say, which were conducive to the to only carrying those paraxial rays. The aperture was not that big, just like I have drawn over here. It's a huge one. But paraxial rays, obviously I can take these closer points closer to the principal axis, and those closer points, they will have the paraxial rays. So that means these rays which are incident at these points closer to the principal axis, they will be reflected, and obviously they are reflected to a single point, and that single point in this case is the focus. That's all we had discussed as of now. But as you can see, this is quite lengthy, or the linear aperture in this case of the spherical mirror is quite large as compared to the previous cases. So now we have a certain rays which are the marginal rays, which are close to the ends of the given spherical mirror. And obviously every point we always tend to follow the law of reflection. So with these normals considered at those points, we can now have the reflected rays to be somewhat like this, and similarly somewhat like this over here. In my case, the diagram that I had taken, considering the angle and the rough hand diagram, I'm getting it almost there, but nevertheless it's at a different point, and this one that was previously obtained was at a different point on the principal axis. So this difference, let me just differentiate between the two rays with a double arrow for the second set of rays that I have drawn, and a single arrow for the previous set of rays. Right. Now, in this case, what we find over here is that we have obtained two foci, but that should not be the case, obviously. And the whole lot of rays that will be between these marginal and the paraxial that I've just pointed out with the curly line over there, there will be whole lot of rays which will be between these two rays, that is the marginal and the paraxial, and their foci will obviously be between these 2 points. These 2 points, let me just name them for you. This is Fm, that is the focal point for the marginal rays, and this is the Fp, the focal point or the focus for the paraxial rays. And we can just draw another line which gives me the, I'll tell you shortly what it gives me. Well, it gives me the reflection caustic. That is the point which is connecting the marginal rays to this focal point, or the focal point or the focus for the paraxial ray. So this red line that I've just drawn is known as the reflection caustic, or even the caustic curve. And the point Fp, we call it as the cusp. We call it the cusp, right? And thus there will be obviously a whole lot of images that will be formed between these 2 points, and therefore with not a single point available, the image won't be really sharp, it will be fuzzy. And that is not what we want, do we? So this phenomenon of obtaining the failure of the paraxial and the marginal rays to pass through the same point upon reflection at a spherical surface is what we call, or we term as, spherical aberration. That failure of the paraxial and the marginal rays to pass through a single point or the same point upon reflection. Now, so in order, we obviously have to get away with all these things so that we have a perfect image. And now, the spherical aberration is obviously, as you can see, is actually an outcome of the law of reflection. And what we can thus obtain is that from the spherical aberration that we have obtained just now, we have two foci, and from that what we can get is we have a formula which we can derive, but I won't be doing it right now. That'll be in your university segment, or the +3 and the higher physics segment that we'll be dealing with later on in that series. But as of now, at this level, we just need to get along with the formula. We can show here that Fm multiplied with Fp, that is the focal the foci, the length of the foci in this case, they, when multiplied, you can have coordinates which will have the points of certain values Fm and Fp, and when we multiply that, we have h squared divided by 4r, where h here is the height from the axis of a ray parallel to the axis, and r is the radius of curvature. We have discussed about r earlier as well. So r here is the radius of curvature. So with this formula we can obviously obtain that the spherical aberration is thus directly proportional. This spherical aberration is directly proportional to the square of the height, because as the greater the height, obviously the greater the spherical aberration height, giving us the idea about the aperture length. And so the greater the aperture length, obviously the greater the spherical aberration. Well, but we will definitely require bigger mirrors, which for different various purposes. So how do we get rid of these phenomenon and obtain a particular image, or at least so as to say sharp images? Now that can be made possible by using two types of mirror, and aplanitic, they are called as aplanitic mirror, reflecting surfaces, or aplanitic mirror. And basically those types have comprise of a parabolic mirror, and secondly the elliptical mirror. Now, I'm just going to give you an idea of these two mirrors with the diagrams available, by making the diagrams available over here. This is what we call as a parabolic mirror, because the shape is in the form of parabola. Not this one as of now, but obviously the one we are going to end up with. Now what happens in these kind of mirrors is that obviously this is the non-reflecting part, this is the reflecting side. The rays that are incident at different points in this type of a mirror, this is the central line which denotes the principal axis, and there will be rays which will be incident on it, and all of these rays will strike exactly a single point, and guess what, they will all follow the laws of reflection. They have to, the laws cannot be changed, and with in accordance with the laws of reflection they will definitely meet at a single point, and that is what the parabolic mirrors are all about. And the elliptical mirror, as the name suggests, the ellipse has two foci, but not more than that. Here we already had two foci, but again there were a whole range of focal lengths for the rays which are falling between the marginal and the paraxial rays. But in this case, in case of elliptical mirrors, it will have a somewhat the same kind of arrangement as the parabolic ones, but the shape will be a bit different. It will be completely elliptical in shape. First, let me give you the outline of the ellipse. So this is the outline of the elliptical shape, and obviously will be concerned about this part of it, where this part is in the form of, or a part of the ellipse. And as the ellipse has two foci, so I can just draw or consider both the foci straight away. So when the light is made incident from one of the foci, suppose it is, so this is f1, this is f2, and from one of the foci if light is made incident on the given mirror, on the surface of the given reflecting surface of the mirror, then following the law of reflection it will be reflected towards f1 over here. Well, this is not completely according to the measurements. This is just a rough diagram that I'm giving it to you. Obviously, the mirror that is constructed has the measurements taken perfectly, and thus you have a perfect result. So light from one of the focus will get reflected from the reflecting surface of the elliptical mirror, and then it will be reflected to the point, to the other focal point. So these are the few ways in which the aberration is uh, you know aberration is cut off, and then or we can say it is suppressed to some extent. We have a sharp image rather than a fuzzy one. So the spherical mirrors can thus, with the eradication of such problems, it can thus be used for various purposes. Let's consider a few uses that we can find of the spherical mirrors. To start with, we'll be discussing about the usage of convex mirrors. Convex mirrors are commonly used in traffics to view the traffic, especially the rear view mirrors in your vehicles. The rear view mirrors in your vehicles, if you are riding a bike, you have them on either side, on the right hand side as well as the left hand side. In cars, you have right in front of you. Well, they are simply convex mirrors, although they look to be really flat surfaces. But obviously, as you know, that flat surfaces are simply the a very small portion of a bigger sphere. Just like you are standing on a flat surface of the earth doesn't mean that earth is flat. It is a part of a bigger sphere of which you are using a very small portion. So that is why, although they may seem flat, but they are convex in nature. And why so? Because if you have suppose, let us consider here that you are viewing a plane mirror in front of you. Now what happens is that the plane mirror has a very lesser field of view. Now if you look at it, in fact it's the other way around. If you see an object, the object is obviously viewing you as well. But the diagram here I've drawn is from the object towards your eye. Here you have your eyes looking at the objects which are behind, which are reflecting light from themselves, and here you have a field of view which is this much only. So this is your field of view. But what about the field of view when you are using a convex mirror? In case of a convex mirror, this is obviously a convex mirror, and look at the field of view over here. So you have your eyes right at the middle, just like the previous case. And now let's go the other way around, that we are drawing the from the eye to the edge of the mirror. Now remember, laws of reflection hold good every time. So obviously this is the normal, and with this angle taken, let me take the similar angle obeying the law of reflection. So with that, it'll go somewhat along this line, and so is the case over here. Obviously they are not they will be looking at your eyes, but your eyes will be looking at them as well. So let me draw the arrow the other way around to give you exactly what we are up to. So these objects that are over here, or even over same angle of reflection, so over here, so these objects that are relatively out of your field of view, which would have been out of your field of view, now you have a very, very large field of view, let me name it as a larger field of view when you are using such a type of mirror, the convex type. So these are obviously much more helpful as a rear view mirror. The convex mirrors are also used in shops because of this larger field of view. When you have, if you have visited malls and shopping market complexes, then you obviously everywhere you won't find us. In the earlier days, obviously you wouldn't find a CCTV, the closed circuit cameras, but what you would have found are the mirrors, and they will definitely be having a large field of view, these convex mirrors, uh, which is uh, which is what I've shown you diagrammatically in these two diagrams, just a comparison between the fields of view. And they are also the similar case in double-decker buses, which was the last of the double-decker bus in Bombay was um, stopped, but double-decker buses also had these kind of arrangements where one can see, the downstairs person can see all the top of the deck if someone might have just barged in. So in shops, in double-decker buses, they are also used as reflectors in lamps. A similar concept, instead of your eye in this figure that we have drawn, instead of your eye, if you have a light source over here, so that light source, the light from that source will be not only going in this field of view, as in case of plane mirror, but in this field of view in case of a reflecting convex mirror. And it is also used in the ophthalmoscope. It has a hole in its center and reflects light onto the sorry, it's not about the convex, it's the concave. The concave part, or the concave mirror, that is used in ophthalmoscope, which is ophthalmology is obviously related to eyes. And what happens is that it has a hole in the center and it reflects light onto the retina, because as you know that concave mirrors have real focus, so that is why the light is reflected towards the retina. The lens system of the eyes forms an enlarged image of the illuminated retina, and therefore you have a magnified view, and the doctor can by the doctor through the hole, which helps him to do the proper diagnosis. Okay, now that's a complicated one, but a simple one for you is obviously the shaving mirror. The popular shaving mirror that you have is obviously the concave mirror, because the image is erect, it's virtual, and you may say that why to use it if it is diminished, but obviously you have an erect image in case of a concave mirror when the object is placed close to it, right? So when the object is placed relatively close to it, the image is erect, and it is a virtual, of course, um, and it helps you to have a closer view of your face. Uh, the other way around was not possible, and they are also used as reflectors, and reflectors as in a searchlight or headlights of a motor car to obtain parallel beam of lights. As you know that for a concave mirror, for an illuminated source placed at its focus, the light from this source will be obviously reflected along this line, and so to get this parallel beam of light, They are also used as reflectors. Different types of reflectors, the concave and the convex part. The convex reflectors obviously reflects the light to a larger field of view, so that a larger part of the area is illuminated, while in this case you want to restrict, so different uses as reflectors for the different types of mirrors, so not to get confused with it. And obviously you have trick mirrors. Trick mirrors use both the convex and the concave types. So you have a small image at some place, so your face may be small and your body may seem large. So they are trick mirrors, which trick mirrors are a combination. Trick mirrors that you see in fairs or Meena Bazaars, they are simply a combination of the these type of convex and the concave type. Now, with all the discussions done and dusted for the spherical mirrors, even the plane mirrors and everything, we are finished with the reflection part. What I would like to do is I would like to leave you end this video with a few questions for you, which you can try for yourself. There's a theory, or there's the concept that when a mirror, which is obviously used for reflection, now this is the shaded portion, and obviously the upper side is the reflected portion, and this mirror M dash let it be, if it is rotated through an angle theta, that means M comes over here, M dash comes over here, the angle of rotation is theta. You have to show that the reflected light, there will be a light which will be incident on the surface as per the previous condition. This was the angle of incidence, and obviously the angle of incidence is equal to the angle of reflection, so this would have been the reflected ray. That's okay, it seems pretty clear. But what you need to find is that there's a concept which says that the angle of incidence or the reflected ray rotates through an angle 2 theta when the mirror is rotated through an angle theta. Reflected ray rotates through 2 theta if the mirror, without changing the incident light, of course, direction of incidence of the incident light, if the mirror is rotated through theta. You can try it for yourself, and probably we'll be doing this exact case in the next video, so no need to worry if you uh, do not or are not able to uh, prove this part, but if you are able to do so, then kudos to you. So, and we'll be discussing a few more cases or few more problems, especially with the numerical types. So the next video will be in the numerical segment of the optics that I'll be starting off, uh, which will contain the various types of numericals associated with the reflection part. And thereafter we can move over to the refraction of light, and obviously that is for the later videos. Till then, thank you for watching.